Hello, everyone, and welcome to today's Design News webinar. It's a Tiny World, the future of miniaturization, sponsored by Maxon, MillMax, Performance Motion Devices, and Isometric Micro Molding, Inc., and broadcast by Informa. I'm Daphne Allen, editor of Design News, and I'll be your moderator today. We have just a few announcements before we begin. Our webinar today is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speakers, download resources, share this webinar, and participate in our Q&A session that takes place at the end of our presentation. Our slides will advance automatically throughout our event. And toward the end of our webinar, we will ask you to complete our survey found on the right-hand side of your screen. Please take a minute to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. Lastly, if you're experiencing any technical problems, please click the Help widget found at the bottom of your screen, or type your issue into the Q&A area, and we will be glad to offer one-on-one assistance. Now, onto our presentation. It's a Tiny World, the future of miniaturization. We're seeing miniaturization trends in nearly every industry, especially in medical, consumer electronics, aerospace, and automotive. That means that miniaturization of components, motors, drives, and more has become increasingly critical for design engineers. I'm really excited to have two experts with me today to discuss these trends and the future of miniaturization. I'm very pleased to welcome Donna Bibber, CEO of Isometric Micro Molding, and Prabhakar Gowrisankaran, Vice President of Engineering and Strategy at Performance Motion Devices. To learn about our speakers, please visit the bios widget. I have a few questions for Donna and Prab today, and we'd love to have you, our audience, send us your own questions. Before we get started, though, I'd like to have Donna and Prab share a little bit about what they're doing and their companies are doing in miniaturization. Donna, I'll turn it over to you.
Thank you very much, Daphne. Thank you for putting on this event. So a little bit about Isometric Micro Molding. We are an innovative micromolders and micro-automated assembly company, really focused on medical and drug delivery device. As you would imagine, the name, we make very small parts with micro features and tight tolerances, micro-sized parts that fit on the ridge of a fingerprint. We're vertically integrated, and where we have a lot of experts in design for manufacturability, design for automation. Been in business since 1990, and we are ISO 13485 certified. So some of those components, as I said, that the experts work on here internally, micro-molded components and assemblies can be micro features, tight tolerance, or extremely thin walls down to 1,000, so 25 microns. We also have 3D printing in-house that helps us to create very small devices and fast devices, fully automated systems that on the back side of the molding machine, we can take it as far as it makes sense. Materials expertise is certainly important here with respect to implantable and selecting the right material. We also have resorbable active ingredient, silicone and fluoropolymers. And our specialties are really in sharps, so micro needles, barbs, microfluidics diagnostics, and sensors and wearables. So what is micromolding? As I said, they can be, this fractions of a plastic pellet. So here's a plastic pellet here. I think you could see my cursor. It's sitting on the side, and the part it fits in the fingerprint ridge. So that's obviously micro. The one next to it has a 6 thousandths diameter on one side and the 12 thousandths on the other side, obviously micro because of the size of it. What's not so obvious are the other two parts here that have 250 micron channel that goes all the way down to the one in the lower left has a 250 micron channel that goes all the way down to 3 microns. So it just trails off to nothingness. So you can imagine the steel that made that core, that plastic channel is micro, 3 microns wide, 3 microns deep, and is the risk to that project and why somebody would go to a micro molder versus a conventional. so extremely small. And then how we measure that channel is also a key. The other one over to the lower right is a 5 thousandths wall polycarbonate needle array, and you can see the curved needles there. At the very end of its fill, it needs to be sharp. So that's really difficult to do, and is really enabled by tooling in this case. So as I said, this is the fastest way we know to get parts in hands that are actually micro as well and scalable. So we're going to look at it before we print it and do some DFM and DFA to make sure that our customers can get something as close as possible, as fast as possible to the scalable device, which means sometimes making printed parts or printing molds that we're shooting the intended design material in. That's very big, and we've been very successful at that the last few years. Lastly, here is one more slide after this was CT scanning. We've been an early adopter of this technology and have had it for about 10 years. So this is really taking an X-ray of the part and creating a first article inspection in 15 minutes. So it's a really powerful tool to get our design of experiment with real data in 15 minutes for all of those dimensions on a fair. It also allows us to see inside the part, as you can see that kind of MRI type view that sees bubbles or inclusions in the parts in that same 15 minutes. So it's been extremely helpful to address our customers' clinical submissions with these STL files that they then use to go back into their FEA assumptions. So really, really helpful. Lastly is automation, kind of bringing them all together, all that data with 16 cameras of this, 32 of that, 8 of this, and all that DOE input, and that full factorial of error still needs to be 1.33 CPK. So it's important to kind of have control over all of those inputs, really looking for a micron in each of them to be successful. So that's just a little bit about us. I'm looking forward to your questions, and thanks very much. At this time, I'll pass it over to Prab.
Thanks, Donna, for that intro. Actually, it's very impressive, the capabilities you guys have in terms of the isometric molding part of it, how small you can print. We are not at that scale, but in terms of controls, we are still miniaturized compared to where we were before. So I would just give you a quick overview of PMD and then just a quick highlight on what miniaturization is for us. So PMD is, we've done motion control. We started off with chips, and then over time, we've grown into adding digital amplifiers and drives that you can co-locate with the motor and fully control the motor. We also do multi-axis motion control boards. And our claim to fame is our C-Motion SDK. So you can, in the embedded world, especially in medical and lab automation, we provide the CSDK, so they're 90% there in terms of what they want to design for controls. We've been used by most of the large lab automation medical guys, and we are also ISO 9001 and 13485 certified. So just to give a quick view from our viewpoint, comparing to what Donna does, which is a tip of a finger, this is a little bit bigger, but relative for us in terms of power density. So the one on the left is the drive that we had maybe 5-8 years back. This is like 25% of the size, and it's double the power density. So it's like 1.5 inches by 1.5 inches. So it really enables you to co-locate these drives. So these have full controls. It has our motion chip and has the power amplifier to drive up to 1 kilowatt worth of power. So these are used broadly in lots of applications. So one of the benefits we have is we not only work in the lab automation medical side, but also in mobile robotics, warehouse automation, semiconductor. So we are able to kind of take all the benefits from all different industries and kind of apply it to the motion control side. And it's amazing. The table on the right we did an analysis in terms of what the weight of the motion controller is in terms of overall automated systems. It's like 1% of the weight. And there's a drastic reduction in the overall volume that we've been able to get to. And just a quick highlight what it does. So it's it has a power connector on one side and digital connections. So it does, you can talk to it over Ethernet or CAN or lots of different communication protocols. And it has the amplifier and motion control, the power amplifier side of it, and a heatsink. So you can fully control a motor up to a kilowatt. And the other new capability in this drive is there's a CPU that's available for the user to download code into. So we've seen that being used in handheld medical applications where they can have all the code running on the drive and it's battery operated. And so it's helpful in surgical robotics and a few other applications. And just as a quick example, just to give you a visual view of what the size looks like. So if you look at one of these collaborative robot arms, so you can locate this drive right at the motor, and all your wiring is power and a network, either CAN or Ethernet to each of these drives. So you can daisy chain a bunch of nodes together and kind of control them together. So that's just a very quick synopsis. Obviously, the scale is very different from what Donna's talking about. That's truly miniaturized. It's super tiny. In my past, I did 3D printing, so it's amazing how thin walls you can print. In our motion control world, we're still pretty small for the power density that we tend to drive. People are amazed that we can drive a kilowatt from such a small unit. Back to you, Daphne.
Great. Thank you, Prab, and thank you, Donna, very much. I do appreciate you guys setting the stage today for us to talk about miniaturization. As our audience can see, you are both offering, slightly different viewpoints into what miniaturization is. But I was wondering if we could start our conversation off right now about talking, what industries are you seeing miniaturization take off, and why?
I can take that one, Daphne, if that works. So the hot markets right now in miniaturization are diagnostics due to self-care, for example, and that really was prompted by COVID. A lot of those things now that people want to get results at home, those types of tests are being developed, and a lot of them require, say, microfluidics, for example, to create that product. Another one is robotic surgery, everything getting smaller and smaller, having to fit down through note surgery, and devices that are minimally invasive and can go around corners and have a lot of functionality to them and still be really tiny. Ophthalmic, things that go in the eye with the aging population, of course, being needing some type of optical help with their eyes. That is becoming extremely big, and it's also a space within the body that is now getting to the blood-brain barrier, which before was very challenging. Now they're going through the eye and finding ways to do that. So sensors are also extremely hot as well. So anything that requires a sensor, whether it's a vehicle backing up, that's a different market. But Industry 4.0 and gaining data has really prompted a lot of sensors, which would be metal and plastic married together with respect to insert or overmolding. So those are some of them that I see here at Isometric.
Yeah, just to add on to Donna's comments, I think we see a lot in lab automation, like Donna talked about microfluidics. We have one application where they took our IC, it's a pretty small footprint IC, and they put it on a pipette control. It's probably the size of half your finger, and it's a card on every pipette. And they're able to actually control each of those individually, and then they tie it back to a central controller. So they're able to get super small sizes with our chips. And in terms of drives, we see a lot like mobile robotics. And so it's a question of size versus power density. So if you can get to the kilowatt in that tiny size, then you can drive a lot of different stages. So we see it a lot in surgical robotics, lab automation, but we also see it in mobile robotics.
Okay, excellent. Now, you've each talked a little bit about how, your work is getting smaller and smaller, right? Um, I'm wondering, is this, are we continuing to get smaller? Is that the goal? And, is there a limit to how small each of you, see in your respective roles or industries?
Yeah, I can start on this. I guess we know the famous Moore's law. So it'll asymptote at some point, but we are beneficiaries of the smartphone market, right? If you see, they're putting so much more in a chip that's small, that's handheld, and we are just users of. So all the chip technology is advancing at a fast pace, and on the power amplifier side of things are getting smaller. It's all about heat dissipation. How can you do the same thing in a small footprint? That means heat is going to increase in that small footprint. So we'd have to work on how to get heat out of it and stuff. So I think it'll keep getting better because we're starting to use mainstream electronics and ICs. But at some point, I think it'll slow. Maybe Donna's at the cutting edge of it, so she can talk more about it.
Yeah, I think, every time that I think we've kind of made the smallest part we can make, somehow we're making smaller and thinner parts. So the thinnest that we've been able to mold recently is a 1,000th thick, 25 micron, which is even just 2 years ago was unheard of. Long and thin. So it's not just the tiny size, it's also precision. And that precision enables really high aspect ratio parts. For example, a cannula that we make for insulin delivery, is over an inch long and has a 160 micron wall thickness, or 6,000ths ish. And so that long and thin, again, a few years ago would have been, there's no way we can mold that, because if you're injecting that and trying to push at 40,000 psi of injection pressure at 0.01 seconds, you can imagine how challenging that would be to fill it all the way to the end. And oh, by the way, it's a fluoropolymer. Oh, by the way, it's PEEK, which doesn't like to be pushed to those limits. So yeah, it's not necessarily just small size, which is certainly getting smaller, but it's precision and single micron, like I said, that full factorial, because that really helps us all to get the top of that value pyramid, right? For that intellectual property, that platform that is challenging, that there's only so many ways or so many people that can make that. And I think that's really where miniaturization is getting really exciting, is the high precision and how we're able to create devices that fit in fairly small spaces. So it's continuing to get smaller and smaller and tighter tolerances.
Right. You mentioned the high precision and the expertise that goes into, micro molding, very thin walls. Is there anything else you need? Are new materials needed to help you continue to, get smaller?
Absolutely. There are materials being developed all the time that maybe have, better melt flow rates that can, flow the long and thin, less gassy materials. There's just so many new grades now that there were, again, only 2-3 years ago. I think the other one, and Prab, you can certainly speak to this as well in your world, and that is to dissipate heat. Because as things get smaller, the microelectronics, for example, you're now in smaller spaces, and that heat needs to be dissipated. And so those materials also need to last for a very long time in that heat. So those are some of the challenges, I think, with we're working very closely too with our material suppliers to say, hey, what do you have that's new? Because those are the things that we stay advanced with, to make sure that we have that in our toolbox ready when we need it. So
yeah, we see a lot of innovation in heat sink materials and the way we do even our construction of our power card. typically we used to make a regular PCB. Now we make an aluminum substrate. So the PCB is printed on top of aluminum substrate so that all the power, the ones that are carrying high current, are all cooled at the source. And the chips are getting smaller, but they do run like 400 MIPS, let's say. So they're going to start dissipating heat, even though they're shrinking. So there's a balance in between how much you can make it smaller and still get the power output through it. Because in some applications, we see they do active cooling, so it's not a big deal. Making it smaller, they can cool it. But there are passively cooled applications where there's no fan, it's sealed. You still have to be able to run through all the temperature range. So it's a balance. And I think I think there's a lot of innovation even in our side on the amplifier side. There's gallium nitride, there's newer technologies that are coming up with EVs that are pushing the boundaries and amount of current that they push through the battery, through their systems. Hopefully we'll start gaining. So we are benefiting from smartphone advances, now EV. So slowly things will there'll be newer technologies invented that'll make it a lot easier.
Okay, excellent. I also want to talk a little bit about, the manufacturing effort to, get down to these miniaturized parts and in some cases, micron-sized parts. Maybe each of you can speak a little bit about, how manufacturing is able to achieve these miniaturization feats, and what you need for further progress.
You can go ahead, Donna.
Okay, yeah. So what we need besides materials is equipment and software, automation, and really human technical skill, because in our experience we have a 40-person mold shop, for example, that is really the enabling technology to doing all the micro molding and automated assembly that we do in-house. And that technology and that type of person, that mold maker, that very highly skilled mold maker, is not something that you see on the market very often anymore. And so we have to balance the human skill with software and with new equipment that can do some of those same things, because as those folks age and then go off to something new in their career, that poses a problem for us to kind of keep pushing that envelope. So that new equipment with the software that can do those things that in the old school way of things is sometimes the technical skill of the mold maker with the skill of the CNC equipment we're able to achieve. So that's what I see from our world. Again, that the automation too, I think the skill really of how to build that piece of automation. For example, our smallest part that we're making as an assembly, that is 3 1,000ths diameter wires, which is 25 micron diameter wire, and they're positioned within 1 micron positional accuracy of one another in an 8-station rotary in a very fast time frame. So that skill set to do that is certainly something that we need to bring people in that know automation, but now we need to teach them micro automation, because that's not something that they've probably seen in some of their previous career jobs. So combination of software, equipment, people, and the skill set to use all those things to create some of these miniaturized devices.
Yeah, we see very similar case in our side. There's a lot of automation that helps us get to these smaller sizes. There's also a lot of inspection and after we assemble it, is the end part accurate? So there's a lot of post-inspection, post-assembly inspection and tests. So there's a ton of software that's written to kind of automate some of these things so you can actually test them, especially being ISO 13485. It's all about the process, right? How repeatable can you make this? And can you produce the part the same way over and over? So there's a ton of automation and software that we have. And to Donna's point, we were able to rely on experts before to make them by hand and do things. But when you scale, it becomes a challenge. So you have to get to automation to get to that repeatability level.
Right. And I imagine the equipment you're each dealing with or using is precision equipment, right? And in some cases custom. So, could you talk a little bit about, how you're working on equipment to be able to deliver these small parts?
Yeah, I think in our case, like for the chips we sell, right, we used to program them one at a time or bank of 5 at a time. And we partnered with companies to automate the whole. So it's a pick and place. So you load a whole tray of chips and it automatically picks, programs, verifies the chip, labels it. So there's levels of automation that have gone up. One, to increase the throughput, but also minimize the errors. Because if you start doing stuff manually, it's not as repeatable as you want it to be. So we're starting to see, we tend to partner with the guys who make pick and place and kind of give your requirements and try to leverage what is available commercially and add a little bit more customization to it in terms of software to be able to use that piece of equipment. And in our case, we get used in these high precision equipment, like we are in microscope stages that do nanometer precision or picometer precision. So we are supplying chips into equipment that's actually it's a full cycle, helping us make the chips we make. So.
Okay. That's interesting how you're, both a user and a customer, right?
Yep.
Of equipment advancements. So. Okay.
I could add a little bit to that too. I agree that it has to be automated all the way through, but there are people that are programming those things, and I think that's really where the skill set comes in. Is also learning how to use those pieces of equipment and program them such that you can achieve the one micron positional accuracy at the end, and we typically, as our subject matter expertise is creating micromolded parts and devices automated. And as I said, that full, if you take your kind of histogram of things with working backwards from tolerance, just say you have a plus or minus 8 micron tolerance, for example, you still need to be 1.33 CPK. So how do all those inputs, whether it's molding process, mold, tooling itself, the automation, the number of fixtures in the automation, the fixture-to-fixture error, and all, like I said, all those full factorials, we have to work backwards for this plus minus 8 micron to achieve a really tight window. And so it's very important with a PFMEA that's really, really precise and goes down to submicron to get micron. So I think that's our challenge. And when you mention inspection, for example, Daphne, we use CT scanning. And so we're, as I said in one of my slides, we're using that to inspect product because it doesn't see the error of a fixture. It doesn't have gauge R&R human error. It has, somebody programs that, and therefore we have the best possible gauge R&R to reduce that part of the process. So there's a bunch of those things that I said there, but they all stack up to minimizing the risk and getting 1.33 and sometimes 1.67 CPK required for some of these tiny devices.
Right. Yep. Yeah, it definitely sounds like having control of the process and a window into that process through and quality control technology certainly plays a role in achieving success. So, Prab, did you have anything to add about maintaining inspection and quality control levels and
Yes, we try to automate some of the inspection. Some of it is measured, but it's to Donna's point, if it's manually done, then there's human error. So we try to put as much automation in the inspection side as we can.
Yeah. Yep, makes sense. I wanted to turn a little bit to the design process, or as companies are designing miniaturized products, whether it's for the diagnostics and medical device space, or the robotics, or automotive, or electronic space. Do you see any challenges that designers are facing when they're designing these miniature or micron-sized items? And what are some solutions to help designers, and how can you support them?
Yeah, I do see that. Most projects that we see come in, or let's say CAD files and drawings, aren't ready to be made yet, and that is because a lot of designers aren't sure that it's even possible to make a part that's a thousandths. They might even say, I'm not even going to go there. So I think the challenge is educating what is possible, and not the traditional, it can't be that small. And so that's an educational challenge, and getting in front of people like we're doing here to raise awareness of, hey, this is possible, and it's scalable, and it's economical. I also see that, again, the expertise in being in a culture, or partnering with somebody that has a culture of submicron, is really key to designers to have an understanding and a risk mitigation hat that helps them with DFM and DFA. So that kind of collaboration back and forth is really key. We don't know form, fit, and function of that device, but we know design for manufacturability and design for excellence. So that collaboration is really important. That openness and transparency is really important to be successful.
Yeah, we see that a lot. We are more like a motion control partner, right? So because we work in so many different industries, so someone, to Donna's point, someone may have solved it in one industry, right? And then they haven't seen it done in their industry. And so when they come to us, we can kind of help them with what a solution would look like. They're still architecting their product, but you give ideas of, oh, these are things you could do. This is the level of precision you can get to. This is the speed and the power that you can get to. So those are things. It's all about education from a design engineer point of view. I'm a designer, and typically you tend to go to what's your comfort zone, what you've done before, and what you know can be done, so you can deliver the project in time. But sometimes you need partners like Donna and us to kind of say, oh, these things have been done in the past, and show an example of how they solve the problem. And that becomes a new tool in the toolkit to say, okay, next time I'm doing a project, we want to design this. So it's a pretty collaborative effort, and we tend to learn a lot from our customers of unique things that they've done with our product that we didn't think was possible, and vice versa. We kind of help them with some of the synchronization they can do across axes and things that are more system level. So it's fun to be in the space we are in.
Yeah, it definitely sounds like collaboration and partnering on projects is important, right?
Yeah.
Yeah. So, well, excellent. Are there challenges faced when engineers are working with other parts or sub-assemblies that are not miniaturized, or have to interact with these miniature parts or micron-sized parts?
Yeah, I can speak to that. So let's just say, for example, again, I'll go back to that. I always go back to that because that's something that is in our culture. But if we're breaking down, where are we going to find a micron, for example? We would be looking at multiple lots of a purchase component, for example, because one of those might come in if you've got this, one of them might come in here, nice and tightly controlled, but it's on the high side. Another lot might come in nicely controlled again, but in the middle and over here. We can deal with that because we can create a shutoff for each of those. What we can't do is deal with a lot that comes in and takes the whole thing up, because that creates error and too much of it to track and follow through our process. So it's that type of mentality that we that might work for conventional that won't work for micro is really dialing in the purchase components and making sure that they shut off just as well as the molds that we're creating or the automated fixtures that we're creating, and they fit nicely with that. It's really it's a key to find those sources that have that culture already, and screw machine parts maybe we don't have, and pulling those in. I think really finding those people that do that and do that well is really important.
Yeah, we see it all the time. Like they would redesign a machine, right? Let's say a lab automation diagnostic machine. They're working on one section where they're going to make it smaller, but the rest of the stuff is still the previous generation. So say the really big motors or PLC or older control styles. But everywhere you have to start somewhere. So the goal may be to just miniaturize one portion of it in the design in that product. And the next cycle of the product would be a much smaller version of it. So we've seen it a lot where customers would start as an experiment on one piece, go to as small as they can build it, still be able to fit it into the existing product, and then use that knowledge that they've gained to kind of rethink the new products that they design.
Right. Excellent. Well, it seems like we're already getting some great questions in from our audience. And I definitely want to leave time for these questions. So I think what I'm going to do is I'm going to ask some of these. But before I do, I just want to let our audience know, in case you haven't posed a question yet, please type your question into our Q&A box. And it's the text box located to the right of the presentation window. We are going to try to get to as many questions as we can today, but if we don't, our speakers will take a look at your questions and get back in touch after our event. So definitely we encourage your participation, audience, and welcome your questions. Before we do begin our Q&A, though, I do want to make sure our audience is aware of our webinar survey. It is also on the right of the presentation window. If by chance you've closed the survey, you can reopen the widget by clicking on the icon at the bottom of your screen. And thank you very much for completing this survey. Your feedback and participation allows us to serve you better. So in terms of the questions, I actually have a question here for you, Prab. Is PMD a product or engineering service company, or both?
Yeah, so we are actually primarily a product company. So we sell chips and drives and boards that are standard. But what we tend to see is they'll start using the standard products and they would come back to us with custom requirements. So we would tend to do custom firmware and software to solve their problem. So one example is, let's say they've designed an instrument where the encoder is not at the motor, it's further out, and they want to try to make it look like a more expensive, highly accurate encoder. We would put custom algorithms in there with feed-forward compensation, things like that that are software-based, that we could then customize our chips and drives and add that custom software. So we tend to engage with large OEMs where they'll take our standard product, we do a DK, where they can quickly evaluate the product and then say, okay, these are the things, it works really well, these are the gaps. And then we have a technical discussion to say, okay, how do we close that gap and what do we need for custom features? But we're not a pure engineering service company in the sense we don't do boards and stuff for OEMs. We partner with design firms that know our products really well and have done products in that industry, and then we kind of connect the dots and help them get to the end point.
Okay, excellent. Donna, what is a typical turnaround time from concept to product and production for micro molding components?
Well, we've gotten amazingly fast at that just recently using the 3D micro printing. So our fastest was 20 hours. So we went from printing the mold and molding parts in the intended material in 20 hours. And it looked something like this. You probably can't tell that from looking at it, but they were 6,000 diameter micro needles. And so now we can quickly and even tandemly take a mold and another mold and print those together, and then have those iterations very quickly and obviously very inexpensively because they're printed. Now, when we get all the geometry and all those kind of iterations flushed out, that's not a scalable process. So we would then go to stainless steel mold in our traditional method. But all that work has been done now to kind of flush out as many risks as we can using that. So that's typically, say, 8 weeks to getting first off tooling samples in the scaling process. So, but very fast iteration is really important to move that along as quickly as we can.
Okay, excellent. And another question for you, Donna. Do you deal with materials that are approved by FDA for dental applications?
We do. FDA, it's a kind of a misnomer, because if it's implantable, for example, there are only maybe this many families of materials that are predicate materials. So they're 10993, they have a master device file, and so on. If it's just a dental, something going in and coming right back out again, those can be a much wider spread of material. So it really kind of depends. But yes, we're familiar with both implantable applications. One is a sensor delivering a drug in a tooth, and others are just instruments that are used in whether it's cleaning teeth or burrs or those types of things. So depends on what you're looking for. If it's FDA, assume it's the small amount of options there.
Okay. Thank you. We have a question about measurement, and perhaps this might be to both of you. This audience member would like to have an idea of the tolerances and dimensions of such small parts, and how do you measure them?
I can certainly take that one. I think it'd probably be best if I just pull this up. I'm going to push this to the audience here. So we use CT scanning. I don't know if you were at the beginning of this, but maybe if you weren't, you could see that the part is actually right in front of an X-ray, and there's a fixture, and it rotates in front of there, creating a point cloud. It's very slow. Sometimes takes 15 minutes. Rotates, gets the point cloud, and you put it over the perfect solid model, and you get this color deviation plot. That is an extremely great way to measure tiny parts and very quickly get a first article. There are other methods, however. We have several Keyence systems that are 28,800x magnification, so it's near SEM quality that we're measuring. The channel that I talked about on that tiny part that's 3 microns wide by 3 microns deep. That one requires like profilometry, for example, to see what's inside there with respect to surface. But, single microns and submicron to some degree, because again, the tooling has to be submicron to make the microns. Both of those need to be measured accurately so we know what we're starting with and that we can troubleshoot and create the solution.
Yeah, we see similar use case, not the CT scan, but they do 3D scans of, like to Donna's point, they take a golden sample, mm-hmm. and then you're kind of doing a comparison, right? And then doing the deviation chart in terms of which dimensions are off. There are some that are a little bit harder to measure. In our case, like if you make a drive, how much does the pin stick out? If it varies based on the amount of epoxy that the operator put in. So there are things that certain angles are harder to measure, but overall we tend to lean to 3D scanning and things like that. We typically do much more of the measurement on the first articles. Like when we first build them, we do a lot more inspection. And then we rely on the process. We're saying, oh, this, and then we do once in a while checking kind of thing. Because of the volumes we have, it's hard to check every drive that we ship out. But we tend to try to prove that the process that we've set up is correct for it.
Okay, excellent. I have a question, Prab, for you. Something you mentioned in the discussion we just had, and I think, Donna, you commented on this as well, and that's the topic of heat dissipation. Prab, can you speak to the innovative heat dissipation you've developed related to 1 kilowatt control in such a small footprint?
Yeah, this is the slide that kind of explains. So what this drive actually has 3 cards in a stack. The bottom card is a power amplifier card, and that has an aluminum substrate. So the nets, the wires are all printed on an aluminum substrate. So everything, the MOSFETs, all of them are dissipating through that bottom aluminum substrate. And so when they're making like a mobile robot, they would put it on the bottom surface. So as the robot is accelerating, it's cooling itself. And it's tied to the metal plate at the bottom. In a larger machine like lab automation, they would just tie it to one of the bigger metal sides so they can dissipate the heat. So because heat's the key, so we can get to, as long as you have a metal surface that you tie into, it can do up to 20 amps 40C. And then we have kind of a derating curve. Depending on how well you cool your machine, you can get higher current output from the drive. So the innovation is all in the power card that we do, because that's where the high currents are flowing. And then you have MOSFETs that are switching, that are dissipating heat. They have to dump it out somewhere. And this aluminum substrate technology kind of helped us solve that problem. So the next amplifier we designed, there may be newer techniques that we use to solve it. And there's newer technologies that are available in terms of the power amplifier parts that dissipate a little bit less heat. So it's a combination of design plus the way we manufacture it.
Okay, excellent. And I know you work on different technology, Donna, but is there anything that you've seen that could help with heat dissipation in your world?
Yeah, again, getting back to those materials on, when we're talking about plastic parts as well as metals. For example, this one, there's a lot going on in this machine. It's an 8-station rotary. And so we already had to do this even for just a piece of automation we're building. But if you can picture, it's the part itself is literally fits on the fingerprint ridge, and it has 3 1/4 of a hair size wires that are placed onto a substrate. And so there's 8-station rotary with all that heat of a wire and, laser welding wires, compression welding. And so we even in the process of creating the part itself, we have to dissipate heat. We have to dissipate humidity, airflow. We also have to dissipate vibration because any one of those environmental keys will throw that off, because you're talking about a positional accuracy of those wires to 1 micron. So in our world of where we, again, manufacturing, we have to do that. But in the world of the customer DFM, DFX, we're selecting materials that will help do that as well. I think it's really important for that conversation to occur, where here are the criticals for making this part, and then having your supplier and your partner help you solve those.
Yeah, great. Thank you very much. Thank you both. Donna, I have another question for you. What 3D printing technology do you use to prototype at micro scale?
We use a machine called the Worth. There's also a Zeiss machine as well that does that. So it's to 0.1 micron resolution, and again, we're taking that part spinning it and putting over a perfect solid model. And that color deviation plot that you kind of see here shows, if you can see a couple of purples at the bottom there, well, cavity 6 and 7 weren't quite the same as the rest. And so we get to see that within 15 minutes. So now our design of experiment, when we're out there molding at the press, in 15 minutes, we get to see what were those influencers of the process that affect the critical to quality inputs. And then rinse and repeat and keep rinsing and repeating until we understand our process window. That's very accurate and very fast, because the old way is wait 3 days for a first article to come back, and now your thought process is kind of gone. So it's really important to, when you're talking about microns, to understand the process and get the inputs to it as quickly as we can. I hope that was what the audience member was looking for there.
Thank you. I appreciate. Another question for you, Donna, regarding the micro molded needle. Is that feasible at high volumes, and what is the smallest gauge available now?
Yeah, our smallest needles are about 100 microns high, and that's obviously dermal, not sub-Q, and very, very sharp, having sharpness of 2 microns at the very tip, 2 micron radius. So very small down to that scale, up to the one I showed earlier is about, I would say, 180 microns tall and curved. That one actually is used for wound care, not necessarily delivering a drug. However, we have put 3/4 of a hair size core pins in each of the centers of other needle arrays, so that it is delivering a drug with kind of a drug soap membrane for capillary action. So yes, they absolutely are scalable as molded parts, and we're very, very good at it. We're doing a lot of it. For a while, micro needles weren't a method that somebody went to, and I see that in the last few years. It's really come back as a drug delivery method that of prominence.
Okay, excellent. Prab, a question for you. Is there a path to buy for low volume and then later move on to build for higher volume?
Yeah, so typically the large OEMs, what they want to do, or even startups, right? They want to do a proof of concept, demo the whole machine. And so they tend to buy these DK boards, which have these drives, so they can just hook them up in their lab. So they tend to buy for lower volume, buy the cards or the drives. And when the volumes go really high, 1,000, 10,000, 100,000, they would then work on redesigning it for cost. So they would take our chips, which run the same software as the drives and the cards, and they can build their own custom board with their own form factor. So a lot of the large OEMs tend to do that. And they tend to get to a diagnostic machine or a surgical robot or a mobile robot quickly to prove that they have solved all their problems. And then later on, when volumes go up, so up to 1,000, the drives make a lot of sense. They are solderable drives. And about that, they would then say, okay, let's take this and design it with the PMD chips. So that way the software that they're running stays the same. So we see that often. So that line between build to buy depends on the end machine they're making. If it's a big, like a semiconductor, they would tend to stay with the buy. They would just buy the drives. But if it's a mobile robot that's going to be in hundreds of thousands, they would tend to build their own at the later point.
Okay, great. Thank you. Donna, we have a question regarding tooling. How does the tooling cost compare to conventional size molding?
I would say it's very similar to conventional or macro mold making. We try to have everything run unattended, as you would imagine, and through automation. So that helps us to mitigate the costs. And the cost is a solution, just as all the other solutions that we talked about was, intolerances and so on. Cost is still something that we need to mitigate because some of these projects wouldn't get off the ground without being nimble in that area and efficient. So it's always something that we're looking at. How do we do things more efficiently? Which is why we've investigated and invested in 3D microprinting as a method to speed that up and still get the right answer as quickly as we can. It's really important to that early work that we're doing. We are wearing that DFM hat and that scalability hat to get to the level of, one cavity is scalable to 16 cavity, or one cavity is scalable to, 32 or whatever. Also, in this example that's on the screen, how do we create an automated system that's smaller but has a few really key systems on there or stations that we can then go to several equipment manufacturers to understand how theirs is going to work here. That then is scalable to the next level. So it's always about mitigating risks and making it economical before we take the big leap to where it gets costly. And I think that is the best method to reduce the cost.
Okay, great. Thank you.
Yeah.
I think we're nearing the end of our Q&A, but I just wanted to ask each of you if you could, take a moment just to explain what's next, for each of you in miniaturization.
Yeah,
Donna?
in our case, in PMD's case, it's more pushing the boundaries, right? You saw the inch and a half doing a kilowatt worth of power. So one axis we see is getting more power out of the same footprint or smaller. The other axis is a lot of new technologies in terms of interconnectivity, in terms of the host communication to the drive, all these encoders that are super high precision encoders that are coming out. So having all these interfaces on the drive to be able to talk to newer technologies. And the progression is obviously getting to smaller and smaller chips. So the chips we sell now work for 90% of our customers. They want it smaller, but still do double the functionality of what we do now. So that's a challenge we'll always keep working in terms of trends towards newer chips that kind of do more in less.
Excellent. And Donna?
I think it's really about continuing to push the envelope and research what's out there that's going to help us do that. That's something that we've been very good at since 1990, as we started making molds, and 2008 started making automation that were continually to push us up the value chain to our customers. 3D microprinting, CT scanning, what's next with materials, what other equipment is out there that can help us to mitigate the risks. And it's constantly researching those new materials and what we can put into our toolbox to help our customers better. We're always the early adopter of those things, which is great. We're having to learn all those things, and then how do we use them? So we've got 10 years in CT scanning, we've got 3 years in CD and 3D microprinting, but always looking at what's next, because those industries are moving so quickly. Okay, what other materials can we be using that maybe last longer and make 100 shots instead of 2 when we're printing them? So really important to kind of keep that in front of us and keep researching to keep pushing that decimal point to the right.
Okay, great. Thank you. I really do appreciate both of you today explaining so much about the sectors you're working in and your capabilities. Very impressive. We do have a few audience questions left that we haven't gotten to, but since we are at the end of the hour, our speakers will definitely get back to you. I think there is some follow-up questions on microneedles and more. Our speakers will be in touch. So thank you very, very much to our audience for joining us today and posing some very thoughtful questions.
Thank you.
Thank you. Definitely want to thank our sponsors today, Maxon, Milmax, Performance Motion Devices, and Isometric Micro Molding. We sincerely appreciate our sponsors' support. We definitely thank our audience, and sincerely, Prab and Donna, thank you for sharing your expertise. It's greatly appreciated.
Welcome. Thank you, Daphne. Thank you, audience, as well. Great questions.
Thank you. And to our audience, everyone in our audience will be receiving a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who may not have been available to listen to our event. Our webinar is copyright 2023 by Informa. The presentation materials are owned and copyrighted by Informa Markets. The individual speakers are solely responsible for their content and opinions. On behalf of our guests, Donna and Prab, thank you very, very much. Have a great day, everyone.
Thank you, too.
Thanks.